Welcome everyone. So this is our 65th live stream geometry. And so today I wanted to mention something special. So I don't usually do advertising much on my channel, but there's this one other YouTube channel that I really like a lot. It's called the Chefs of Problem Solving. It's created by an IMO medalist, and he has some really fantastic videos. So I really encourage you guys to check out his channel. He does a really good job of explaining the solutions to problems, and he's really passionate about math in general. But he just created a program called the Shef Scholars. So people interested in Olympiad math, not just geometry, but all kinds of Olympiad math. Yes, he's an IMO medalist. So they can join this program for free, and kind of similar. I don't know exactly how it's going to work, but I suppose it's going to be similar where you can chat with other participants. So his name is Zlatko Salko. I forget exactly what country he's from, but I'm going to put the link to his YouTube channel in the description of my video, and the link to the new program that he's starting called Shef Scholars. So it's spelled SHEF''S. And so any of you interested in Olympiad math, I would definitely recommend checking it out. All right, so today I am gonna go over problems from the Baltic Way Shortlist. So I did problems before from that were actually on the Baltic Way contest, but I didn't take problems from the short list. So the Baltic Way, it used to be just Estonia, Latvia, and Lithuania, but then over time, more countries have joined, Germany, and a few other countries. I think Iceland was joined at one time, and sometimes random countries besides them also participate. All right, so I'm going to get started. Share my screen. So it's actually a team contest. I forget exactly how it works, but it's not like an individual contest. You work together as a team and solve the problems. So here's the first problem I chose. So you draw the three X centers of triangle ABC. Maybe it would be better drawing these as lines instead of segments. So we have ABC, and then let's draw the X centers. So now I can just draw the angle bisectors. Actually, you know what? Let me draw at least a point on each side like that. And then I'm going to see where the angle bisectors meet. And those will be the X centers. All right. So this is IB. This is IC. And I guess we only really need to prove it for 2 out of the 3, right? So I could call this IB and this IC. I'm just going to label the other one, but we don't have to use it for now. So this is IA. And we want to draw BIA. So I'll start with the other two. So CIBA and BICA. We want to draw the Euler lines of those two triangles. So yeah, let me hide a bunch of stuff here because that's all I really need. So actually, let me draw the point F. Sorry, I'm just trying to make this look nice. Okay, so IB and IC are the X centers. And yeah, this line BC is too long. So let me shorten it. Okay. There we go. So here we have the triangle. IB and IC are the X centers. I'm going to draw in the X circle, or the two X circles. There we go. That's one of them. Here's the other one. This is the angle. This is an angle bisector right here. And we want to show the Euler line of these two triangles. Those two Euler lines meet on the circumcircle ABC. So I'm going to draw the circumcircle. I guess maybe a better way to do it is we draw the two Euler lines and we let them intersect, and then we show that that's cyclic. So let me draw the Euler lines. So first the circumcenters. Let's see who else is on. Thanks for joining, Con. So now we have two cons. Whoops. I want this and this. And then I'm going to draw the orthocenters of those two triangles. And then here's the other one, and then I'll draw the intersection of the two. Oh, whoops. Let me change that to be a line instead of a ray. So yeah, this almost looks like it passes through point C, which so I'm going to move it around in just a second. But here's the two Euler lines. And maybe that looks a little bit better. So this point O, I'm going to rename it to P, just to not be confusing. Basically, we want to show ABPC is cyclic. All right. Let me shrink this diagram a little bit, or see what I can do. Okay, I want P to be at the bottom, ideally, but there we go. That maybe looks a little better. All right. Oh, it looks like K and L lie on the circle. I feel like that's going to make things quite a bit easier now that we know that. So first, can we show, so K, is that obvious? That K and AB, KC is cyclic? In-center, external lemma. Yeah, you're right. So yeah, let's draw that and this. I see Animal just joined. And these concur at the in-center. Call that I for the in-center. I'm going to just rename this I as Q. Thanks for joining, Animal. Good to see you. So this is our first problem. So yeah, K is going to be the midpoint of arc AB because we know that KA is equal to KB. And the same is true with L. And so, well, we know that KA is equal to KB. But yeah, that's just obvious by the in-center, x-center lemma. Okay, so we want to show MK and LN intersect on the circle also.
Triangles AB, I sub C and AI sub BC are similar, so the angles between the corresponding lines will be same. That will be equal to 90 minus half angle. So
Okay.
that implies it.
All right, so that solves the problem because they're similar triangles. So the angles between corresponding parts have to be the same. So it didn't even have to be the Euler lines. It could be kind of any lines that correspond to each other, right?
Euler line is helpful in the fact that these are midpoint of arcs.
Okay, so we had to use that. We had to use that K and L lie on the circle. But I guess M and N didn't have to be orthocenters. M and N could have been any other kind of corresponding points, right? Is that true? I think that's true. So like if M and N were the centroids, then would it also work? Yeah, let me check that out before I type it up. So like if M and N are centroids, let's say, or yeah, let me check it out. So like let's say I think it's just true in general. So it's what is let me pick a different triangle center. Yeah, all the triangle centers lie so close to the line. For example, I could try picking the in center. And let's say I adjusted the picture just a little bit. So like, I think then like Rn and I'm sorry, LR and KO would also meet on the circle. So LR and then K, yeah. So yeah, it didn't even have to be the orthocenters. It really could have been any corresponding points. Okay, so I'm going to write that out. It's true because, yeah, any two corresponding lines in the triangles are gonna make the same angle as the angles between the sides of the triangles. That's kind of true by homophoties. Yeah, we have two different cons on the session. Okay, so I'm gonna type this up. So let K and L be the midpoints of arcs A, B, and AC. Oops. Of the circle ABC. So by the in-center X-center lemma, K is the circumcenter of AICBI. And L is the circumcenter of AIB CI. All right. And then so yeah, K and L lie on the circle because yeah. Now then we have basically by an angle chase, those two triangles are similar. So yeah, so I'm just going to write out the triangles that are similar, but yeah, it's an easy angle chase. ABIC is similar to ACIB because angle IBIC, or sorry, angle IBAC equal to angle IBIC, which is equal to angle ICIB, which is equal to angle ICAB. I'll say, and so on. Okay, so that's a pretty standard angle chase. And then, why didn't this, oh, I need another $sign. All right. I think we can prove it just making it clear. Okay. All right. I'm going to copy what Con wrote and put it here. Okay, yeah, so you wrote it out in a little more detail here. All right, so this is like the full proof right here. And then I'm just gonna write it like abbreviated right here. So let me see. So basically the angles between corresponding parts, or I'll say corresponding lines in similar triangles, are the same as the angles between their sides. And basically that's kind of the proof up there. So the angle between MK and LN is the same as the angle between yeah, but basically we want to show it's 180 minus A, but it's the same as the angle between yeah. So it's the same as the angle between okay, now I'm kind of confused. Oh yeah, it's the same as the angle between AB and AIB, right? So the angle between MK and LN it's the same as the angle between, what are two corresponding sides of this? So AIC and AC, right? Actually, now I'm trying to figure it out. So wait, are those two triangles oriented the same way? Sorry, let me check something here. Sorry. Because they can't just be similar, right? They also have to be oriented the same way. So but I think, yeah, it looks like they are oriented the same way. So I'm guessing angle IBAB. Hold on one second. Let me make sure I understand this. So basically, I think we're saying this angle NPK is equal to this angle, right? Yeah. Somehow I think this should be 180 minus Well, yeah, it would be the angle between line AI, yeah, ICA and AC. Which is the same as angle IBAC. And we want to show that's the same as, which is, so yeah, IBAC we want to show that's 180 minus KAL. But IBAC, that is 90 minus A over 2. Okay, I think I got this. Which, yeah, basically we want to show that's half of this arc, which is equal to, yeah, which is equal to arc B over 2 plus arc C over 2. For and that's equal to arc B over 2, or I'll say AB over 2 plus AC over 2, which is equal to arc KAL over 2. And so this implies that P lies in the circumcircle of ABC. So and then we can make the same argument using point IA. So argument with, I'll say with triangle BIAC. So the Euler lines of those three triangles concur on the circle. So I'm going to move on to the next one. Yeah. Let's see who else is still on. Okay. All right. Sorry about that. So that's the first problem. Here's the second one. So yeah, so this is another one from the Baltic Way Shortlist. So we have a triangle ABC with in center I, and then we draw the three midpoints. Okay, so I is going to be the in center. And then MA, MB, MC are going to be the midpoints of the sides. Just doing some renaming here. This is I. This is MA. So maybe the IM lemma will be helpful here. MB. This is MC. K is the reflection of I over MA. All right. And L is the line through K parallel to BC. So we have a parallelogram here. We define P and Q as the intersection of that with MAMB and MAMC. So we're going to define P and Q. This is P and this is Q. And we want to show the X circle of PMAQ goes through the AX center of ABC. This is kind of random. Is this just like, because they look similar, I wonder if this is just some homophily thing. Right? So these two triangles are similar because they have, all three sides are parallel. Okay, so we want to draw the AX center. Let me draw these as rays. So okay, let me start by drawing the X circle here. Yeah, I wish there was a faster way to draw X circles, but so is K the altitude from F to PQ? I think that might be the case. Yeah, it looks like it. Looks like K is the altitude from F to PQ. I don't know if that's obvious. And hide these for now. And so we want to show that the AX center lies on this circle. All right, let me draw the AX center. I don't know if it's worth just using the in-center X-center limit here, but I'm just going to draw it the usual way. Yeah, so we're saying those two intersect on that circle. So really, we just need to calculate the angle between these two and show that it's the right amount. And do they pass through the tangency points? It almost looks like they do. Yeah, it looks like they pass through the points of tangency of this with NP and NQ. So there's a couple things here that we have to prove.
I is the naggle point of the medial triangle. So K is the foot of F on PQ.
Okay. And it almost looks like JK is a diameter. But how did you figure that out? How did you figure out that K is the perpendicular?
M sub A PQ and the middle triangle are homothetic, so M sub A K is Nagle-Stevian.
Okay. So yeah, so it's by homophily. I guess it might be worth. Do we want, well, is it obvious that BL and CM meet on that circle? I guess we could calculate the angle between those two, and then we could try to calculate angle LKM and show they add up to 180. So yeah, how do we calculate angle? Well, angle LKM, yeah, that should be easy to compute because PKL is isosceles and KQM is isosceles. So yeah, I think it's not hard to show that this is cyclic by angle chase. And then, so you mentioned that FK is perpendicular to PQ. Would that solve the problem? Okay, so yeah, okay. So first we let these two angle bisectors meet a point J. So that's the AX center. Then we show that KLJM is cyclic. And then well, so first of all, is it obvious that angle BCM bisects angle BCH? I think there's a few things here that we still have to prove. So does MAB equal MAL equal MAM equal MAC? I think it kind of looks like that, right? Yeah, I think that's key. So is that obvious?
We can prove that CJ passes through the tangency point M of that circle.
Okay, how do we prove that?
So I'm gonna prove that angle KJM equals angle KJC.
Okay.
So we have KJM is equal to KMQ.
Okay.
KMQ is like half of angle MAQB.
Yeah, okay, so we can calculate that angle.
Yeah, and similarly we can calculate KJC, I think.
KMC.
Oh, wait,
yeah.
We don't know that they are clearly, right?
Okay, so I'm gonna write this out step by step. I think we have a lot of things we've discovered, but I think by writing it out, it'll make it clearer, like what we know and what we have to prove. Okay, so we know, oh, Hakan just wrote, we know F, J, and K are collinear. And by the homothety of M, A, P, Q, and ABC, we have IJ is parallel to MAF. Okay. All right, let me write this out step by step. So I'll say let L and M be the points of tangent C. Of the MAX circle of triangle MAPQ with sides MAP and MAQ. Okay, so that's the first step. Then let J. So we're defining J to be the AX center. And then we could calculate angle. Yeah, I'm just trying to find the right order to prove things. Okay. I is the Nagel point of MAMBMC. Okay. So I think that's important. So yeah, so I think that's, yeah, I'm gonna write that out. So I is the Nagel point of that triangle. So MAMBMC is homothetic to triangle ABC. Okay. So yeah, I think that's a key idea. Of the X circle of, okay. So then so let F be the X center of MAPQ. So yeah, so once we know this, then we know that FK is perpendicular to PQ. And okay, so now we're going to show angle FJM is equal to angle FJC. So angle FJC is just 90 minus angle BCJ, which is angle C over 2. So yeah, but do we know that FJ and K are collinear? Let me see. So BK is parallel to CI. Oh, okay. KM is parallel to CI by the homophily. Yeah. KM and B are perpendicular to CJ. So K is the orthocenter. Yeah, there's a lot of stuff here. Let's see. But how do we know J? How is K? Or the foot of the altitude. So I think basically we know BK is parallel to IC because IBKC is a parallelogram. And we also know that KM is parallel to IC. That looks like just an angle chase. Intersection of MC and BL is the antipode of K. Because K, L, and C are collinear and parallel. Okay, so first we prove K is the orthocenter by showing C, K, and L are collinear and it's perpendicular. Okay, so yeah. Actually, if we can show that MAL is equal to MAB, then that would also prove that K. Okay, but I kind of like how. Okay, I like how GEO King wrote it up. So yeah, let me delete this for now. I'm gonna write what GEO King said. Clean it up a little bit. So BK is parallel to CI. Since BICK is a parallelogram. That's where we use this fact that K is a reflection of I. Since BICK is a parallelogram. Okay. All right, I'm gonna fill in the details in just a second. So K, L, and C. And C are collinear on a line perpendicular to BJ. And so KM and B. Oh, I have to be careful with copy paste. It gets messed up the format. And KM and B are collinear on a line perpendicular to CJ. Okay. All right. So yeah, I'm gonna clarify this in just a second. All right. So when I say KM is parallel to CI, yeah, I mean, I think that's kind of obvious, because we know MK is parallel to the bisector of angle MAQP. I'll just leave it like this. So yeah, so KL and C are collinear, and KM and B are collinear. And yeah, so K is the orthocenter of BCJ. So J, F, and K are collinear. Okay. So actually, this means that KLJM is the X circle. So yeah, KLJM is cyclic. Well, yeah, we also want to use the thing about the Nagel point. Yeah, K is the tangency point of the, yeah. So yeah, we're finished here. So J, F, and K are collinear on a line perpendicular to BC. And so that solves the problem. So the X circle opposite MA of triangle PMAQ goes through the A X center of ABC. All right. Sorry, it took me a little while to write that up. I'm not as fast as you guys, I'll admit that. So I will move on to the next one. Oh, this looks kind of interesting. So we have a cyclic quadrilateral where A, B, and CD are not parallel. Let me use this. And then we want to draw the midpoint of CD. Let me draw it so C and B are on the bottom. So all right. A, B, C, D. And M is the midpoint of CD. And P is a point so that PA equals PB equals CM. So I'm going to draw the perpendicular bisector of AB. And here's the compass. Oh, but I need, yeah, like this. Okay. So this is going to be point P. And maybe it's worth drawing the center of this circle. So, because that would lie on both perpendicular bisectors. So yeah, I'm going to call it O. We want to show that AB, CD, and the perpendicular bisector of MP are concurrent. That's kind of interesting. Okay, so here's point P. So PA equals PB equals CM. And then we want to draw the MP. And let A, B, and C, D intersect somewhere. Sorry, I don't want P and O to be too close. How do I make P and O farther apart? Whoops, sorry, someone just joined. Okay, so if I make it like a tall, yeah, there, that looks better. Okay, so something like this. Almost looks like an isosceles trapezoid, but whatever. Yeah, maybe like that. Okay. So, but A, B, and C, D meet at a point. And we want to show the perpendicular bisector of MP passes through that point, which is kind of the same as saying EP equals EM. Okay. Thanks for joining Blue Hawaii. I don't like this cyclic quadrilateral. I feel like it looks too much like a trapezoid. Let me see if I can make it look better. I kind of like that better. Let's see if I can. Shrink things just a little bit. I kind of like that. So yeah, PA equals PB equals CM. How do we use that fact?
I think you should swap the point C and D because it is a quadrilateral ABCD, not AB DC.
Oh yeah, you're right. Good point.
I think drawing the circles centered at P with radius PA and the circle with diameter CD can help.
Okay. So I'm going to draw those two circles. And they would be the same size, right? So maybe E lies on the radical axis.
The radical axis is just the perpendicular bisector.
Okay.
And that is true because of by Radix theorem. So we are done.
Oh yeah. No, this is a fast one. Okay. There's one problem that looked a little bit harder. I'm gonna do that one after this. But yeah, this was kind of an easy one. Yeah. Okay. So I'll say let omega P and omega M all right, let me do a harder one after this. Be the circles with centers P and N and radius PA equals PB equals MB equals MC. Okay. So since both circles have the same radius, then the radical axis is the perpendicular bisector PM. axis is the perpendicular bisector of PM. And EA times EB equals EB times EC. That means that E lies on this radical axis. So that solves the problem. So then AB, CD, and the perp bisector of MP concur. Let me just define E up here. Let E intersection of AB and CD. All right, so that was a fast one. So there was another problem. I'm not. It looked like it might be hard, so I will try it. This one right here. But who knows? Maybe it's not as hard. So I think it was later in the shortlist too. So I think the ones that are later in the shortlist might be harder. It has a really weird notation. So let me make this array. And so we have 3 collinear points. So this is, sorry. This is D sub A. So yeah, I don't know how they came up with this notation. This is E sub B. And this is F sub C. And maybe it kind of makes sense actually. So then we have a DB and DC are on BC. So so we could call this DB. And let me draw the parallel segment. Let's check the chat. Yeah, it is weird notation. So that's DB and DC. So yeah, there's a lot of arbitrary points that you can choose in this figure. Like DB can be any point we want, I guess, on the side BC. And then EC is on CA. So ECFC and EA DA are parallel. Yeah, so what if I draw it kind of like this? So that BEC. So ECFC and EADA are parallel, like that. And then we draw the last one. So FADA and FBEB are parallel. Okay, so let's okay, so FADA is going to be a line like way over here. So maybe I'll make FA like this point. So we want FADA to be parallel to FBDB. Okay. That looks a little better. Okay. So this is FB. And then we want to show the midpoints of EAFA. So I'll call it MA, MB, and MC. So EAFA, EBFB, and ECFC. It's kind of interesting. Hold on just a second. Okay. So EAFA. Oh, I don't even think I did the right three. I might relabel them, just hold on a sec. So EAFA, FDDB. So it's really this midpoint. And then DCEC. Okay, so I didn't even really do the three right midpoints. So it's really those three midpoints. DCF. Yeah, it's a weird configuration. We can relabel them if you want. I'm just not sure. Yeah, how do I make the points farther apart? Maybe some. Oh, I feel like this is a good point to move. Kind of like that. Yeah, this is tricky. It kind of looks a little like the Gauss line, right? I feel like it has to be like a generalization of the Gauss line.
Actually, it looks a little like ERIQ lemma. Maybe
Okay.
we can create, do you know ERIQ lemma?
Yeah, so I think, so the ERIQ lemma, it's kind of like, let's say you go a third of the way from G to J and a third of the way from H to I. I mean, basically, so yeah, it's like a generalization of the gliding principle. So, like the midpoints of these three are collinear, right? So, well, actually, in this case, we know MKOL is a parallelogram, right? So it's kind of obvious that MN and O are collinear. But like for the ERIQ lemma, like even if K was like a third of the way instead of half, and L was like a third of the way, it would still be true.
Yeah, and I think it also works if G, J, and HI are diagonals. They don't have to be necessarily two sides of a quadrilateral.
Okay. So it's true if they're diagonals too. All right. Well, let me see, I wonder if these three are collinear. No. Okay, so yeah, like we have ECBC and BBFB, so those are both midpoints. So then if I went like a certain percentage of the way, yeah, I think it could be used. I don't see right away how it would work, but it looks like it could be useful. Let me call these like X, Y, and Z, just so you don't get confused. Or, yeah.
Can you check if the three circle of with the centers X, Y, Z are coaxial?
Okay. Yeah, that's a good point. I think they might be. Actually, I don't think so, because sorry, someone keeps messaging me. Yeah, no, I don't think they're coaxial. Hold on one second. All right, sorry about that. Let's see. Okay, yeah, so you were asking about those 3 circles. Looks like it just requires Thales, but in a nice way in general. This problem or ERIQ? Okay. So how do you do this problem with Thales or ERIQ? We can't. Is it obvious to all of you how to solve this one? Oh. Yeah, we can move on if you guys want. Do you want to move on? All right, I'll move on to another problem, but we'll come back to this later. Oops, sorry. All right, so